4 of the only equations that we've been working with are linear equations with constant coefficients, right? Yeah, so a general linear equation can have variable coefficients, so any function of x. So the reason we haven't done much with them is if you have random functions of x as coefficients, then it's very likely that you're not going to be able to find a solution. So it's not to say that they can't be solved. If you're interested, we're going to skip chapter 6, but in chapter 6, rather than finding an explicit function as a solution, you can find series solutions of differential equations. But generally speaking, if you have non-constant coefficients, it's going to be very difficult to find a solution. But there happens to be one class of equations that has non-constant coefficients and always has a solution that we can write down in terms of elementary functions, like sine, cosine, polynomials, and so on. So we'll see in chapter 5 that equations with constant coefficients have many practical applications. These equations are really just for fun and for the novelty of being able to solve equations with non-constant coefficients. So even though these are different from the equations that we've been studying so far technically, the fact that they all have solutions really boils down to the fact that they're equations with constant coefficients in disguise. So with an appropriate substitution, they can be transformed into equations with constant coefficients. So that is the reason why these all can be solved. Okay, so these equations are called Cauchy-Euler equations. Down the general form. So a sub n, so this is some constant, okay, multiplied by x to the power n, and then multiplied by the nth derivative of y. So this is the standard form for these equations. What is the pattern that you notice?
The power of the coefficient is the
right. The power of x is equal to the derivative of y. Okay, that's what makes these Cauchy-Euler. And we're also going to require that x is positive. Okay, so this requirement is in order to guarantee existence and uniqueness of the solutions that we find. Okay, so the strategy that we're going to use is much like the strategy that we use for constant coefficients. What is the strategy that we use for constant coefficient equations?
YC.
Yeah, so, yeah, so we need to define the complementary function.
Trial solution?
Yeah, so we use a trial solution. Okay, so for constant coefficients, then we use a trial solution. What is the trial solution? Y equals e to the mx, right? And what's the reason for that? Well, I mean, you take several derivatives of this and substitute, all of the derivatives are constant multiples of e to the mx, right? So after substitution, there's a common factor of e to the mx, and since it's non-zero, you can divide by it and solve for it. Right, that's why that works. Okay, so for Cauchy-Euler equations, we will also use a trial solution. Okay, and here the trial solution is y equals x to the n. Why do you think this is a good choice for a trial solution? Can you imagine what would happen after substituting? Let's write the first few derivatives. So y is x to the n, okay? M is constant. So y prime is what? mx m minus 1, okay? Second derivative, m minus 1, x m minus 2. Let's do one more. Third derivative. m minus 1, m minus 2. Multiplied by x to the n minus 3. What will happen if you substitute into one of these equations? You can basically ignore the constant multiple, right? So whatever this is, it's constant. You see what will happen? What do you mean will cancel? So the key thing that makes the Cauchy-Euler equation a Cauchy-Euler is that the derivative equals the power of x. Okay? So each term, the power of x is equal to the derivative of y.
Square, you can cancel out x to the n.
What do you mean? Cancel?
I mean, if they're all, if each of the derivatives has an x to the n minus whatever term, they're all gonna have x to the n times x to the minus whatever that is. Factor on x to the n.
Every term will have a factor of x to the n.
Yeah.
Right? So if you substitute y, then this has degree n. Right? If you substitute y prime, well, y prime is something multiplied by x to the n minus 1, right? But then multiplied by x gives you x to the n. See, so this factor of x is going to restore the power to x to the n, to x to the n, right? So if you take, x to the n, right? Y prime times x is x to the n minus 1 times x, which is x to the n. Okay, so y double prime times x squared. Okay, I'm omitting the constant multiple, but I'm just trying to demonstrate what's going on. So this is x to the n minus 2 multiplied by x squared, x to the n. Okay, so the same sort of thing happens that happened with constant coefficients. There, every term contained the same exponential. Here, every term contains the same power of x. Okay, so then we factor it. Since we're requiring that it's positive, we can divide by it, right? And that leaves us an equation that we can solve for that. So, so as usual, in order to solve an equation like this, what do we need? An nth order linear equation.
Complementary?
You need complementary function, so I guess. How many solutions do you need? You need n, right? So, can you tell? So we're going to also call the resulting equation the auxiliary equation. Can you tell what the degree of the auxiliary equation will be? It will be n, right? So like if you check, if, say we have a third order equation, then this will give us a third degree polynomial equation in n. Okay, so hopefully that will give us 3 distinct solutions. If it doesn't, then we'll do what we did before and see how to handle multiplicity. Okay, so then after doing that, then we find a particular solution. I'm not sure if I mentioned it when we were working problems in section 4.4, undetermined coefficients. That method really requires that the coefficients are constant. Okay, so since the coefficients are non-constant, the only method that we'll have available to find a particular solution is variation of parameters, what we talked about last time. Okay, so let's do what we did before. Let's consider the second order equation first, and then I'll tell you how to handle higher order equations. So okay, so the first happens to have 2 real solutions. So this is a Kosher equation. Power is 2, derivative is 2. Power is 1, derivative is 1. Power is 0, derivative is 0. Okay, so be careful not to mix this up with the others, okay? So, again, constant coefficients, remember that it's based on the trial solution of an exponential. If you have the Cauchy-Euler equation, it's based on a trial solution that's a power of x. Okay, so, let's see what the resulting auxiliary equation is with this trial solution. So always pick y equals x to the n. Okay, so then y prime is n x n minus 1, y delta prime n minus 1 x n minus 2. Okay, so if we substitute right, so like I mentioned, so the powers of x are restored. So 2 derivatives reduces this by 2. But then after multiplying by x squared, it's restored to x to the n. Okay, so n times x to the n minus 8 x to the n equals 0. All right, so every term has a factor of x to the n, so let's factor that. Okay, and then here we have m squared minus m minus m minus 8. Okay, now because of this requirement that x is positive, that means that x to the m equals 0 has no solutions. Okay, so I guess instead you can divide by it. All right, so that leaves us with m squared minus 2m minus 8 equals 0. Okay, so this factors n minus 4 and plus 2, 0, so n equals 4, and n equals minus 2. Right, so this solution to the, right, so this is called the auxiliary equation. Okay, and I guess before I say anything else, what do you notice, how does the auxiliary equation compare to the differential equation? Similar, right? The coefficient of the first term and the last term are the same, but the coefficient of the middle term is different, right? So, whereas with equations that have constant coefficients, it's easy to move directly from the differential equation to the auxiliary equation. Since the coefficients are different here, I would recommend making the substitution every time. Okay. All right, so these are the solutions to the auxiliary equation. What does that mean for solutions to the differential equation? M equals 4 means what? Y equals x to the fourth is a solution. Okay, and then same thing here. M equals -2, so y equals x to the -2, also a solution. Right, so what are we looking for? Not just two solutions, but two linearly independent solutions, right? These solutions have to be different enough from each other. It's pretty easy to check with two functions. How do you check if two functions are linearly independent? If they're not multiples of each other, then they're independent. So clearly here, they're not multiples of each other. So we have two linearly independent solutions to a second order equation, homogeneous. That's enough to write the general solution. Okay, so the general solution. Y equals C1 x to the fourth plus C2 x to the minus 2. Pretty simple. Okay, so this is the best case, right? Distinct solutions. The next best case is two repeated real solutions. So one solution, multiplicity 2. It must be a real number. How do we handle repeated solutions when we have equations with constant coefficients? Say one solution is e to the 4x. The second solution is
X
times e to the 4x, right? Do you remember, so I did it one time and then I said you can just use this rule from now on. How did we determine that that's how you handle repeated solutions?
multiplicity? No?
Not linear.
If you know one solution to a second order equation, how can you determine the second linearly independent solution? Use the formula of reduction of order, right? So I'll do it one time again, and then from now on, you guys can use the fix. So the next equation happens to have one real solution. Okay, so same trial solution, y equals x to the n. Okay, so with the substitution, we get, so the same thing will happen, right? So these are all going to be x to the n, right? So this will ultimately be n minus 1 x to the n, right? And then this would be minus 5 times m x to the n plus 9 times x to the n. Okay, common factor of x to the n, we can divide by it. That gives us the auxiliary equation n minus 1 minus 5n plus 9, which is n squared minus n minus 5n makes minus 6n. Okay, so this factors as m minus 3 quantity squared, so m equals 3 multiplicity 2. Okay, so this gives us one solution, y equals x to the third power, right? Okay, so to determine the second linearly independent solution, we need to use reduction of order. Okay, so again, I'm going to appeal to the formula. You remember what the formula is?
U times x to the third.
What's that?
U multiplied by
I'm not going to use the method, I'm just going to use the formula.
Oh, the
It's y1 integral,
E to the negative dx.
yeah, e integral negative p dx
oh,
over
that's what I learned it the first time.
y1 squared dx. What is p for this problem?
Negative 5.
X to the
Almost.
third.
Oh,
This is, yeah, let me write it this way, this is y1
Negative 5x.
close.
minus 6.
To identify p, you have to write the equation in standard form. In other words, divide by the weak coefficient. Okay, so in standard form, this is y double prime minus 5 over x, y prime plus 9 over x squared, y. Okay, this is p. Okay, so y1 is x cubed. E integral negative 5 over x divided by x cubed squared. Right, so this is negative 5 log x. Over x to the 6th. Okay, what is this? Wait a second, I've got a double negative, right? P is negative, and then this is
Supposed to be
negative, so
negative.
it's this, so.
So it's
it
technically
should be
positive.
This, okay. Now, what is this?
1 over x and
Yeah. Bring
X
this
to the
up,
fifth, that
remove the
cancels.
logarithm, it's x to the 5th.
so it's
Okay, so it's x to the 5th over x to the 6th.
just 1x. Right?
So altogether, this is 1 over x. Okay, now I don't want to work this out in general for any Cauchy-Euler equation. Let me just say that this is no coincidence. Okay, this will always happen regardless of the equation. So this integral always reduces to integral 1 over x. Okay, so it's y1 multiplied by natural log x. Okay, so this is the second linearly independent solution. First one, x cubed, second one, x cubed log x. Okay, so this is no coincidence. So, like before, if you have a repeated solution, you can find the additional solutions that you need by repeatedly multiplying by x. Now, instead of repeatedly multiplying by x, you repeatedly multiply by natural log x. Okay, so what is the general solution?
Bless you.
Okay, general solution is
C1.
c1 x cubed
C2
x
cubed
log
ln x. That's not bad.
Okay, so like before, you don't need to go through this each time. If you have multiplicity, you can fix it by multiplying by log x. Okay, so if it happened to be multiplicity 3, then first solution x cubed, second solution x cubed times log x, third solution x cubed times quantity log x squared. Question?
Yeah. Could you go the line 3 over there on the first, on the left hand side?
Here?
Yeah, that's good.
So I'm substituting y double prime multiplied by x squared.
Right.
So x squared multiplied by x to the n minus two, if you add the exponents, x to the n.
So the x to the square root.
This will always happen.
reduced.
Every term should contain x to the n. Okay? Two derivatives reduces the power by two, but then multiplying by x squared increases it by two, so you get returned to x to the n. That make sense?
Kind of.
Yeah,
So,
it's always going to
You're trying
happen.
to say that no matter whatever the exponent is, for example.
Well, because of the form of a Cauchy-Euler equation where the derivative matches the exponent. Whatever the derivative is going to reduce the exponent by that much. Like the fifth derivative of x to the n is going to be something multiplied by x to the n minus 5. But in the Cauchy-Euler equation, the fifth derivative is always multiplied by x to the fifth power. So the derivative reduces it, but then the exponent returns it back to wherever it began. Okay, so all that we're really interested in are these coefficients. Okay,
So
just,
minus 2 would reduce the,
yeah, I'm going to multiply this by this, x squared, right? X squared times x to the n minus 2 is x to the n minus 2 plus 2, x to the n. Same thing here. X to the n minus 1 multiplied by x to the first power, x to the n minus 1 plus 1 back to x to the n. Make sense? So this, if it doesn't happen, something went wrong. This should always happen. Other questions?